Okay, hello everyone. My name is Dhruv. I'm a data scientist at Comet, an ML development platform that provides solutions for data scientists and their teams to track, compare, explain, and optimize models across the entire model development lifecycle. So, developing models in the real world is hard, and even the best development practices can be hampered by a lack of appropriate tooling. So for my talk today, I will be covering how Comet's experiment management tool integrates with Spark NLP and how it can alleviate some of the most pressing pain points when it comes to creating ML models. So let's begin with a question. Why is machine learning hard? So a typical machine learning development cycle tends to be presented in the following way. We start with identifying a problem that we can solve with machine learning. We collect some data that we think is relevant to the problem, clean it, we explore the data, and then we build intuitions around the data. And then we move on to feature engineering or building models that can create their own features to help us solve the problem. We then train and evaluate many different model configurations to find one that works well. And finally, we deploy that model to production. Now you'll notice that there are some arrows here that loop back to previous steps in the process. The reality is that any step in this pipeline can influence any of the steps upstream. So really, what the model development process looks like is this. There are feedback loops everywhere. I actually ran out of arrows just because there are just so many. And the reason for this is because machine learning as a discipline is iterative. And it's iterative because we apply to ML to problems where we cannot directly specify an optimal solution. So it's very hard to know beforehand, based on your data and your task, exactly what combination of pre-processing techniques, model architectures, hyperparameters, and evaluation processes will produce a good model. You have to experiment. And the process of experimentation is what leads us to our core challenges. So let's take a look at what these challenges are. At a high level, the major challenges in the ML experimentation process can be broken down into three categories. Problems of data management, problems of model comparison, and problems of trust. So with data management, we know a model is only as good as the data it is trained and evaluated on. This means that when building a model, it becomes necessary to have tools and processes in place that allow us to quickly determine what data was used to build a model, if this data has changed in any way, and if there are any issues with the data itself. As for model comparison, I've mentioned that ML development is iterative. So as practitioners, we will try many different approaches to solve that problem. And these approaches involve tracking many different combinations of model architectures and parameters. And manually tracking these various inputs can become prohibitively difficult. And this is only made worse as the number of people working on a model increases. Finally, we have the issue of trust. In the healthcare domain especially, it isn't quite enough to have a high-performing model. We also need to be able to trust the model's predictions and have methods to reason about a model's behavior if we want to successfully deploy that model to production. So let's dive a little deeper into each of these challenges, starting with data management. Now, in the real world, data is rarely static. The environment in which we deploy our models and expect them to perform is non-stationary. And as a result, our data is shifting in many ways. So what are some of the ways in which data shifts? Specifically, what are some of the ways data shifts in healthcare? So the first type of dataset issue we will talk about is shifts in patient populations and practices. Now, in NLP, in healthcare, the primary source of data is EHR records, electronic health records. And these tend to have quite a bit of variability over time as clinical processes evolve. This means that a model trained on past data might not be able to accurately identify conditions on the latest standards of care. COVID-19 in particular has demonstrated how abruptly diagnosis can change, even though underlying symptoms might not be changing as dramatically. Because someone exhibiting flu-like symptoms in the post-COVID era might not have the flu. And then another thing to account for is models trained on data for a particular demographic of the population might not be applicable to other demographics within the same clinical location or even across geographies. So these shifts need to be accounted for if we expect to be able to use machine learning to aid in diagnosis. So the next type of shift I want to talk about is a shift in data formats and nomenclature. So I mentioned earlier that standards in care evolve over time. And one common task for ML in healthcare is predicting ICD codes, which is essentially a classification problem. These codes are based on evolving standards, and so changes in these codes basically correspond to shifts in your target label. So a model trained on, let's say, ICD code 9, standard 9, is not directly applicable to any data that is using ICD code 10, because there is not a very clean mapping from between codes. So the final type of data issue is related to the quality of the data itself. So most clinical terms do not follow a common ontology. Physicians will often use abbreviations or acronyms. So this makes it very difficult to standardize clinical texts. So for example, the acronym APC in a health record might mean activated protein, C, advanced pancreatic cancer, antibody producing cells. So this can make it very difficult to develop a standard named entity recognition model on this data. There are also typical issues that we see in NLP data, like spelling mistakes, transcription errors, ambiguities around the use of punctuations. In short, healthcare data can be very noisy. And because of this noise, it basically creates a bunch of complications when you're trying to build models. So let's move on to challenges of model comparison. So I mentioned before, developing a model is an iterative process that involves experimenting with several variables. You will most likely try many approaches before arriving at a model that works. And this comparison is much harder when the size of your team is growing and you have multiple people working on a model because they are trying many different things. So that means keeping track of not only what you as a practitioner are trying to solve, but also the approaches that your colleagues are trying. Additionally, single performance metric across an entire data set is usually not sufficient to characterize a model's performance, and we'll see why this is the case. So the first issue of comparison is related to metrics. So when evaluating a model in healthcare, a single metric like accuracy or precision is usually inadequate. This is because when making predictions with a healthcare model, you have to take into account the effects of this model across multiple patient demographics and geographies. So this involves tracking performance metrics on many subsets of data. This means that any given model will have multiple metrics across these different subsets of data that have to be analyzed. So a single model could have tens to hundreds of metrics based on the number of subsets you're evaluating it on. So this brings me to my second point on model comparison. So if you're an individual working on an ML task, it might be okay to manually track your progress using a notebook, a personal notebook, spreadsheets. But as the number of approaches that you try keeps growing, because the number of approaches that you may want to try is not fixed, manually tracking these metrics starts to become quite tedious, especially if you are moving between frameworks. So, for example, if you are building a model, let's say using LightGBM, you are free to use uh, the term L2 MSE, mean squared error, to report the error metric, the regression error metric in the LightGBM model. However, if you switch your framework to XGBoost, all these metrics now get reported as squared error. And over time, this is bound to lead to confusion as to how the metric was computed. The other issue is ensuring reporting standards when you're working with a team. So if you have a large team, more often than not, someone in the team will report a metric as accuracy, someone else might report it as val accuracy, someone might just report it as ACC. So doing this manually is just a very tedious process for everyone involved and quickly becomes very prone to mistakes. So let's move on to the last section of trust. So in healthcare, model performance is usually not the ultimate goal. It is equally important to be able to trust the predictions being made by a model in order to debug issues that might arise from building this model. Now, deep learning has had tremendous success in NLP applications. However, these models remain mostly uninterpretable. And explainable deep learning is still an active area of research. So in lieu of true explainability of these models, it becomes very important that we have proxies for it by making the modeling process as transparent and explainable as possible. So in that way, we have some pathway for debugging these models when necessary. So what do you need in order to trust a model? So at a very high level, trust is a function of three components. Visibility. Do all relevant stakeholders have visibility into how the model was developed? Is it easy for them to find the code, the parameters, the data sets, and metrics that were used to create the model? Reproducibility. Given the information that we just talked about, is it easy for an independent party to reproduce the results of a model's training run? And finally, we have auditability. So given an existing model and the steps to reproduce it, and some predictions from the model, can we trace back why a model might have made that prediction? So with that, we conclude the challenges for effective experimentation. And I know you might be thinking right now, yes, ML is hard. So what can we do to make it easier? So I want to talk briefly about what a tool like Comet can provide to this process and what we do exactly. So Comet provides a suite of solutions for data scientists, enabling them and their teams to track, compare, explain, and optimize models across the entire development lifecycle. So let's see how that works in practice. At its core, Comet provides a Python SDK that integrates with all the popular ML frameworks, including Spark NLP. In fact, Spark NLP now ships with a dedicated Comet logger, making it easy to use Comet ML within your Spark NLP workflows. So by instrumenting the Comet logger into your workflows, practitioners do not have to worry about manually keeping track of their experimentation data. The Comet logger makes this process automatic. So let's see how it works. So here we have an example of a classifier model within a Spark NLP pipeline, and I'm using the Comet logger to monitor the output logs of this classifier. So basically, when we run the training for this pipeline using pipeline.fit, the metrics are automatically logged to Comet in real time so that you can track the training of the model over time and basically look out for errors or anything surprising that might happen. Additionally, The logger also has a convenience method for logging parameters from the pipeline models so that you can log the individual parameters from every stage of this pipeline. And these parameters are logged to your Comet experiment where it's easily available for analysis. Finally, we have this project level view, which collects all the individual experimentation runs. You can easily compare multiple sets of experiments, add any number of custom visualizations, and essentially what happens is you now have a centralized repository for all your ML training, making a true system of record and source of ground truth for your model development process. So let's revisit some of the challenges we talked about earlier, and let's see how we can use Comet to solve them. So the first challenge has to do with data management. Now, if you worked in ML long enough, chances are that you have tried something like this when it comes to managing your data, which involves creating folders for different dataset splits or pre-processing techniques. Over time, this can become very confusing and very unwieldy. So instead of doing that, let's see how we can make use of a tool in Comet called Artifacts. So Comet Artifacts are a tool for dataset versioning and lineage tracking. So it provides a convenient way to fetch, track, and use data within your experiments. So you can see here, with a single line of code, you can fetch a dataset by name and version and download it to a specified directory so that you can use it in your training runs. And when you use a artifact in a training run, it is logged to an experiment. So you automatically have an idea of what input data was fed into a model. Artifacts also support versioning and are available across your Comet workspace. So they are not limited to just a single project. So if you want to reuse a dataset across different modeling tasks, you can, without having to write a whole bunch of custom code to load in the data. Artifacts also support metadata, so you can add any sort of additional context to this dataset. For instance, if you want to add information about where the data was collected from, how many samples are in there, provide links to maybe a data collection page or an annotation page. It can all be done through a very convenient dictionary on the metadata page. And finally, if you want to track data sets that are already in other remote data systems, for example, S3, Comet Artifacts allows you to map these remote data sets within the artifact so that you can track the URLs for these individual data points within your experiment. So let's move on to model comparison. Again, if you've been working in ML long enough, the chances are you've used a spreadsheet to track your model progress. I've done this myself. And this might work if you are just an individual working on a short project. But as time goes on, or if you have to share your work with other stakeholders, it just becomes very, very difficult to effectively have others understand your work. For instance, slicing and dicing your data is just very difficult with a spreadsheet. If you're collaborating with someone, establishing proper standards of reporting becomes very, very difficult. And manually reporting these metrics leads to lapses in tracking or repeating things that other people have tried. So instead of a spreadsheet, Comet provides an experiment table as well as a project level view of all your visualizations, so allowing you to easily filter, group, and slice your dice your data in any way that you see fit. We have a highly customizable visualization tool called Panels that lets practitioners build pretty much any type of visualization that they want on top of their data using JavaScript or Python. You can easily select subsets of experiments to compare relative performance, and isolate and visualize single experiments as well. At the single experiment level, Comet provides a convenient way to diff or compare two experiments. Here we can see two runs side by side along with their reported metrics. So you can compare one model's performance to another. Along with reported metrics, you can also diff the model's parameters. Here, the difference between the two runs is highlighted, so you can very quickly see what parameter was changed between runs. Additionally, we also support diffing source code. There are many instances where a change in model performance can happen due to just a change in the underlying source code and not because of a change in parameters. And this is just a quick way of identifying those changes. And lastly, we also automatically log the compute environment used to run your experiments. So this includes operating system information as well as installed packages in your Python environment. So changes in dependencies can cause unexpected changes in model results. So it's always a good idea to have this information on hand. Comet will automatically track all this information for you. You do not need to specify any additional logging. It just happens on its own. So let's move on to the final challenge of trust. So we'll start with visibility. So in addition to the project page UI, where you can analyze your model data, Comet provides a tool called Reports for basically summarizing your findings. Reports works in a similar way to GitHub README, but in addition to using Markdown text, you can embed your experiment data, visualizations, and any other like equations, and basically provide context around your modeling process, explain design decisions, summarize your findings to all relevant stakeholders. For the challenge of reproducibility, we all know that reproducing the work of others is difficult, even if we have all the information at hand. Comet addresses this challenge by providing a convenient reproduce button for all your experiments. Under the hood, Comet will track the Git metadata for a project and is able to restore your project to the exact commit that was used to run an experiment, as well as displays the command used to run the experiment. So it's very easy to know exactly how to recreate a run. And the final challenge of auditability, I mentioned that Comet provides a suite of customizable visualization tools. Here we have a custom visualization tool for HTML data, which works with the Spark NLP display library. So we've uploaded a bunch of model predictions as HTML files to an experiment, and we can use the HTML panel, which is a custom panel, to look at the individual model predictions. And similarly to how we did the diff earlier, we can compare model predictions between runs, allowing us to spot discrepancies in the model, and combined with the other information, such as the source code, dataset parameters, and model architecture, we can sort of debug the model behavior. We also support, through custom panels, adding model application building tools like Gradio. So Gradio is a Python library that allows you to quickly build UIs around your ML models. And you can embed these UIs directly into your Comet project. So here, I have an image classification debugging tool, which basically uses integrated gradients, which is an explainability algorithm for image classification. Within the Comet project, you can upload an image, and then any uploaded images to this UI will get logged to an experiment, so that you have a record of predictions that you've tried and explanations from the model. And with that, that concludes my talk. So just to summarize, so model development requires experimentation. And this means that we have to constantly iterate on our data and models. Effective experimentation requires rigor, and manually enforcing this rigor is tedious and tends to be prone to mistakes. So, in order to alleviate that, we have to use tools that live where we work. And so that rigor is automatically integrated into the work so that we as ML practitioners can focus on developing models and not on making sure that we are reporting any and all data that could be relevant to the experimentation task. And that's it for my talk. I've included a link to a demo notebook where you can try out the Comet Spark NLP integration, and a link to the Comet website where you can find out more about the solutions Comet has to offer for ML teams. Thank you.